Hi, we at Team ASR are proudly presenting our solution, Mealtime, two native mobile apps to automatically generate meal plans for people with eating disorders and connect them to therapists to make recovery affordable and accessible. Millions of people across the world suffer from eating disorders. These individuals would agree that the mental repercussions that come with eating disorders are severe and can cause long-lasting side effects, such as chronic depression and anxiety, serious mental illnesses, which cause 7,000 deaths per year. Current solutions for eating disorders are temporary. A small proportion of affected patients fully recover from treatments such as rehab and therapy, the most common remedies available today. Apps that aim to assist individuals with eating disorders often facilitate obsessive behaviors by enforcing excessive calorie counting measures and weight loss or gain trackers. So what's the solution? Mealtime is an app that solves the problem of temporary fixes to eating disorders. By gathering data on the user's statistics and preferences, the app trains and fits models to tailor potential meal plans for steady weight loss or gain. Along with meal suggestions, the app includes full, in-depth recipes. Our model of treatment calls for heavy therapist involvement. As such, we didn't want to only develop for the user. We created a separate companion app that therapists can use, which aggregates data from multiple patients and allows them to get in easy contact with their patients. For our app to function, we had to integrate many different technologies together. Our backend is built with Python and runs a fast API server on Google Colab for easy testing. Our front end, which is built on React Native, is able to interact with 5 different backend APIs to serve data to the user. To train our meal plan model, the model is first auto-regressively pre-trained on text data, so the data is self-labeling. We continue our self-supervised learning when we adapt the pre-trained model with contrastive learning to produce text embeddings, a highly compressed form of the text. As you can see here, the first training step involves predicting the next word, thus the term autoregressive. The next training task involves pairing text with text from the same passage and using that as positive training examples. If we read the first text starting with a number and ending with solid state, we mentally store information about the text, and we realize that the first section on the second part matches up to the given text. The embedding model works in a similar fashion where the text is vectorized into embeddings. The training process is easily scalable to any size because we can use the permutation of any two elements as a training example. We use the cosine of the angle between two n-dimensional vectors in an n-dimensional space to quantify how close two embeddings are. In training, the aim is to generate a high similarity between embeddings of two texts from the same passage and low similarity for texts from different passages. Our custom search engine embeds all of the foods and data corresponding with the foods and evaluates the cosine similarity between all of the foods and parameters that we input. Lastly, we utilize the Monte Carlo tree search algorithm to optimize our meal plan recommendations for daily caloric intake and user preferences. Although at first we faced struggles with this implementation, we ironed out the issues, and it turned out to be close to optimal for our intended purpose. Given more possible combinations and ordering of dishes than there are atoms in the entire universe, this algorithm helps us to navigate the high-dimensional search space in an efficient manner to generate an effective meal plan. And now for the demo of our app. We start out by completing a short survey, inputting our age, height, weight, gender, activity level, spice tolerance, sugar tolerance, and any potential dietary restrictions such as allergens. Now we are able to see the current day at a glance. Consisting of just 3 meals total, the user can see the entrees, sides, and any potential fruits that the user might consume with the meal. And now heading over to the Plan tab, we can see the meals that our app's algorithm suggests for the entirety of the treatment period. Clicking on any particular meal for any particular day will bring up pictures and recipes for the associated entree, sides, and fruit dishes. Next up, the Trends tab has graphs relating to nutritional intake for the user's cumulative treatment plan. These graphs are also available to the patient's therapist. Lastly, we have the QR tab. The user's food therapist can scan this QR, and on their own personal version of the app, they have the ability to see the patient's progression. And here we have the app the therapist would use to facilitate the patient's treatment. Starting out, we have a blank patient screen. the therapist must first scan the patient's QR code on the app. After doing so, the patient's treatment information, consisting of the day's meal plan and cumulative nutritional graphs, becomes available to monitor and tweak by modifying the caloric intake parameter. We plan on deploying our app to the public as soon as possible, and we know our app has a long future ahead. Daily meal tracking and a computer vision-based system for analysis of photographic meal input will drastically improve the interactive nature of our app. Additionally, models for chatbots and more extensive peer connections could help build a greater community.